Hey, welcome. Have you ever wondered what exactly stops a faulty appliance from giving you a nasty shock? Well, the answer is this incredible invisible safety net that's running through your walls right now. It's called an electrical earthing system, and today we're going to decode exactly how this silent guardian works to keep you safe every single day.
So to really get why these systems are so important, we have to start with the problem itself. What's the actual danger? Imagine electricity going a little bit rogue, like a frayed wire inside your toaster touches the metal case. Suddenly you've got this hidden, silent threat. And that threat? Well, it has a specific name.
And that name is touch voltage. This right here is the key idea for everything we're about to talk about. It's the voltage you'd be exposed to if you walked up and touched that faulty toaster. The entire goal of an earthing system is to make sure this voltage never, ever becomes harmful. So, what's the magic number? Well, according to the big international standards body, the IEC, 50 volts AC is pretty much the safety limit for us humans under normal conditions. If a fault creates a voltage higher than that, we need a system that can shut it down, and I mean incredibly fast.
So here's our game plan for this explainer. We'll start with that invisible danger, then we'll meet our safety net. After that, we're going to decode the alphabet soup of terms, get to know the main systems out there, and finally, see the devices that come to the rescue.
All right, let's dive right into our first section, the invisible danger. Just remember, everything that follows is designed to solve this one very specific problem, controlling that hazardous touch voltage before it has any chance of reaching you.
Okay, so we've got the problem, now what's the solution? Let's move on and meet the hero of our story, the electrical safety net itself. This is all about the fundamental role that earthing plays. The easiest way to think about it is like an emergency overflow drain for electricity. If there's a leak, that fault current, the earthing system gives it a super easy, safe path straight to the ground. This prevents the metal casing of your appliance from becoming live. And that path has to have very low resistance, because electricity is lazy. It will always take the easiest route, and we want that route to be the safety wire, not you.
All right, on to section 3. To really get a handle on this stuff, you kind of have to learn the lingo that engineers use. And honestly, it's a bit of an alphabet soup, a secret code defined by the IEC. So, you ready? Let's crack this code.
So, the first letter is all about the power source itself. Think of that big transformer down the street. If it's a T for Terra, that means the source is directly connected to the Earth. If it's an I for isolate, it means it's isolated or not connected to Earth. Simple as that. T for tied to the ground, I for isolated. Now, the second letter tells us about your end of the deal, the building or the installation. If it's another T, it means your building has its own separate independent connection to the Earth. But if it's an N for nurture, it means your building's safety wire is connected all the way back to the power source's earth point.
And hey, sometimes you'll even see a third letter, but only if it's a TN system. An S stands for séparé, which means separate. You have a separate safety wire and a separate neutral wire. And a C stands for combiné, which means they're combined into one single wire for part of the journey. So let's meet the actual players on the field. You've got the neutral wire, usually blue, which is the normal return path for electricity. Then you have the protective earth, or PE, that's our safety wire, which is always that distinct green and yellow. And in some systems, you get that combined PEN conductor, which does both jobs. As you can see, those colors are absolutely crucial. You do not want to get these mixed up. Okay, we've learned the alphabet. Now for section 4, where we put it all together to form the words. Let's meet the 3 main systems you'll actually find out there in the world: TN, TT, and IT. So let's put the 2 most common ones side by side. In a TN system, your safety connection is one continuous wire that goes all the way back to the transformer's earthing point. But in a TT system, your building has its own private earth connection, literally like a metal rod driven into the ground that's totally independent from the source. And this table here really brings home the main difference in how these systems actually behave in a crisis. Just look at that first row. In a TN system, a fault creates a massive short-circuit current, which trips a breaker instantly. In a TT system, the current's a bit smaller. But look at the IT system. It's the real oddball. On the first fault, the current is super tiny, and get this, the power stays on. And there's a really good reason for that, which we'll get to in a minute. So to make this a little more real, let's look at probably the most common setup in the world, the TNCS system. You start with that combined PEN wire coming from the utility. Then, at your building's main electrical panel, that wire gets split. From that point on, you have a totally separate protective earth wire and a separate neutral wire running out to all your outlets. It's a really clever and practical compromise. But here's the thing. An earthing system is just a path. It's a road. It can't actually do anything on its own. It needs a partner, a device that can see the fault and slam on the brakes. And that brings us to our final section, the safety devices that actually spring into action. And really, there are three main types. First, you have your overcurrent devices, your classic fuses and circuit breakers. They're the workhorses that trip when there's a huge surge of current. Then you have residual current devices, or RCDs, which are way more sensitive and can detect tiny, dangerous leaks of current. And finally, you have a special insulation monitor that's only used in those unique IT systems. Okay, so let's talk about speed. Think about a common voltage you'd find in a house, something like 230 volts. Now, if a fault happens and that metal toaster case suddenly becomes 230 volts, how fast do you think this whole system needs to react to keep you safe? Less than 5/100ths of a second. I mean, that is ridiculously mind-bogglingly fast. It is literally faster than you can blink. It's not even close. And that's why you need both a great earthing path and a lightning-fast protective device working together as a team. And what's really interesting is that the type of earthing system you have actually determines which protective devices you're allowed to use. For example, on a TNC system with that combined wire, you actually can't use one of those super sensitive RCDs. That's a major reason why that particular system is becoming less and less common these days.
So why on earth would anyone want that IT system, the one that doesn't trip on the first fault? Well, because in some places, losing power isn't just an inconvenience. It could be a disaster. Think about a hospital operating room right in the middle of a surgery, or a critical factory production line. You can't just have the power cut out. So the IT system is a genius solution. It doesn't trip, it just sounds an alarm, giving the staff time to find and fix the problem before a second fault would cause a shutdown.
So when you really boil it all down, it just comes to this. A properly designed earthing system is truly the silent guardian in your walls. Its entire job is to take a situation that could be lethal and turn it into nothing more than the minor annoyance of a tripped breaker.
I know it's a complex topic, but hopefully you now get the language and the logic behind it all. And it really makes you wonder, doesn't it? As you go about your day, plugging things in, what hidden, incredibly fast safety systems are just waiting silently to protect you? Thanks so much for tuning in.